So we're going to turn now, still in the context of early connectionist models, to the question of learning. As we have mentioned a few times, this was a burning interest for many reasons, and not because machine learning was on the horizon, but because we know that brains are changed and modified by experience. Now, the networks we've looked at so far have not had any way to automatically derive their weights. Those weights in the interactive activation networks are handcrafted in order to get the desired relationship between the various levels. And with that, a thinking tool becomes available for thinking about relationships between top-down and bottom-up processing, to use the jargon. Now, you might think it's an unvarnished good to learn the appropriate values from the data. And indeed, when backpropagation was introduced in the late 1980s, this was taken universally as simply a good thing. But one might ask oneself whether it's necessarily a good thing and why it might also perhaps change the modeling enterprise in a bad way. So, put on my enthusiastic hat. Of course it's good. We've got a data set we want to learn. That is an association between inputs and outputs. We don't know the weights. If we have an algorithm that can find the weights, then we can learn that input. Unfortunately, we know that when you do that, you take complete leave of any kind of grounding in biology. We know that the brain does not work like that because there are no teachers, there's no explicit right answer, there's no supervisory God who can say, yes, that's good, that's bad. And so the development of such means that any sets of numbers we can associate, we can probably find weights to map among them. And if we're not aware of what we're doing, we can cause all kinds of mischief by claiming that the results we obtain actually relate to the real world rather than to our model. So that's why one might want to have some reservation. Well, back in these early days, before backpropagation, there was work done on various kinds of learning, and we've met one already, which is Hebbian learning. That is, we met Donald Hebb's intuition that repeatedly taking part in the firing of cell B by cell A will ultimately lead to an increase in the efficacy of cell A in causing B to fire. That vague notion that doesn't speak of mechanisms, Donald Hebb waved his hands a lot, can be given formal implementation in the little rule shown there. This little rule says that the change in one weight, the weight 2i from j, should be some constant multiplied by the activation of the first unit, as the second unit, multiplied by the activation of the first unit. Now let's assume for a moment that eta, the little constant there, the Greek letter eta, is a very small value, because we're going to make very small changes to the weights. If the two units fire together, then AI and AJ are both positive numbers, and so the weight will become stronger. And thereafter, of course, AI and AJ are going to be slightly more likely to fire together. If AI is positive and AJ is negative, then this will produce a decrement in the weight. And following that logic, if both AI and AJ happen to be negative, then that would increase a positive. So I hope you can see what this is learning is correlation between AI and AJ. So if they do the same thing, the weight will tend to grow, and if they don't, it won't. This very simple rule, as it stands, is not enough to build a useful neural network. There's lots of problems. But variations on this rule, which is itself inspired by Hebbian learning, can generate intriguing structures when we create large multi-layered networks. And so it has been explored. It has been called Hebbian learning, although as you can see it's only a specific instantiation of the rather vague ideas in Donald Hebb's postulate. And it forms one of a family of unsupervised learning techniques, many of which go back to the 1960s. One way of remembering this is that units that wire together fire together. It's an associative learning method. If you're only learning correlations, you're learning that this goes with this. And it means that to the extent that we can speak of a network storing associations, such that one thing is likely to give rise to another thing, then similar things will be stored in similar ways. Similar inputs will produce similar outputs. What this method does is it identifies those inputs out of all the inputs to a unit, which reliably influence it, and it tunes the weight to magnify that influence. So formally, we have the change in the weight to unit I from unit j is a function of the activation of unit I and the activation of unit j. The learning rate there is kept deliberately very small so that we only make small changes to the weights. We'll be using something called a learning rate in pretty much every model we use. Now, this mechanism, as limited as it is, has a lot to recommend it. For one thing, it maintains the link to the underlying neurobiology. That is, the change in the synapse is understood as a function of the activity of the two neurons that meet in the synapse. So it only uses local processes, and there's no spooky action at a distance and no God-given controller. It is, however, very limited in what it can learn. It can learn correlations. And in this very simple form that I've presented it here, it's actually unstable. What you'll see is that we've only provided a means to increase the weights. It is the basis for many, I don't know about most, but many unsupervised learning techniques, and we can obtain some interesting and insightful results. Consider this, if you will. Here we've shown a unit which has two incoming weights, one associated with the presence of a tone and one associated with the presence of an air puff. Now, these are based on behavioral data, studying the response of a rabbit to a puff of air on its eyeball. And the puff of air elicits a physiological response. When you puff a little blast of air onto the rabbit's eyeball, it blinks. And when you ring a tone, a bell, it doesn't blink. So what we can show here on the bottom, I've got little green boxes showing when the air puff is present and when the tone is present. And initially we can see the air puff elicits a blink, and the tone does not elicit a blink. By repeatedly pairing the air puff and the tone, however, a Hebbian Learning style update to the weights associated with those two inputs will gradually increase the weight associated with the tone. So we'll go from the situation on the left-hand side, where the tone is very ineffective at stimulating the unit that triggers the eye blink, to the situation on the right-hand side, where the air puff and the tone are of equal efficacy in eliciting the eye blink. This is, of course, an instantiation of Pavlovian classical conditioning. There you undoubtedly have heard of Ivan Pavlov, who trained dogs to salivate at the sound of a bell, so the story goes. Well, here you can see how that observation might be turned into an associative learning model. What's learned here is the correlation between the air puff and the tone. They tend to co-occur. Here's another slightly more abstract example. I generated, I think, 1,000 points. Each point has associated with two numbers, and they're shown here in the two-dimensional plane as a scatter point. And I generated them so that in the data set as a whole, input 1 is correlated with input 2. They have a strong correlation. They're not perfect predictors of each other, but they have a strong correlation, and you can clearly see that we could fit a straight line to these data, and it would have a slope of 1/2, because the input 1 is typically about twice the size of input 2. Now, supposing we had a network like this that accepted these two inputs only. And I've given them two weights there. And let's make the unit that produces an output as simple as possible, so it's a linear unit. That is, we compute its net input, and that is then simultaneously its activation value. That's illustrated by the use of a straight line through the unit. Supposing I pick random values for these two weights, for weight 3.1 and weight 3.2. I'm going to do that 4 times. So we're going to have 4 random starting points. And those starting points can also be shown in the same space because they are also 2-dimensional numbers. So the combination of the two weights can be illustrated as you see here. So the green, yellow, blue, and red dot represents starting positions, random starting positions in weight space. The question is, what happens to these if we go through the data set again and again? I've shown you the first 20 patterns there, but there's 1,000 patterns in the data set. What we do is we go through those 1,000 patterns, taking note for each pattern of these very, very tiny influence it would have on the weight if we were to accord it such an influence. At the end of it, passed through all 1,000 patterns, we then actually change the weight based on the sum of all the suggested weight changes from the 1,000 patterns. We make a small change and then we repeat this. So we go through the 1,000 patterns again and again. We got computers. This is easy to do. What happens is that the weights change, and the change in the weights from one pass to the next is shown here. You can see they all go off and do different things. We're starting from 4 different points. But what you can see is that the resulting weights are not arbitrary. We always end up with weights in a ratio of about 2 to 1, which is precisely the ratio of the correlation. The first input is about twice the size of the second one. So that the weights that we arrive at using this make transparent and are derived from the correlation that exists in the data set. So you can see that Hebbian learning in this simple form learns only correlations. And furthermore, if we go back to those weights, you can see that they're growing without bound. The blue one is becoming very largely negative, and the other 3 are becoming very largely positive, but they're going without bounds. If you were to implement a network model using something like this, you would have to augment it with some means of stopping the unlimited growth of the weights. So Hebb's intuition spoke of long-term potentiation. Long-term inhibition, that is a countermanding process that would also shrink or decay weights if 2 units are not functionally connected, would also be needed. There are other ways to constrain this. Now, you might think that such a simple algorithm would have no place in today's complex world of neural network models. Nevertheless, this simple algorithm is still grounded in biological processes, and it makes use of the kind of information that we assume might be present in brains. And in this respect, it circumvents some of the problems that we will encounter when we turn to supervised learning. It is a manner of automatically uncovering statistical regularities that are implicit in the data. So the weights that were discovered there revealed the correlation present in the data. And there has been work done which attempts to mimic the changes in synaptic plasticity that we see in early stages of visual processing using Hebbian learning, and that has proved to be quite insightful and relatable to a particular school of cognitive neuroscience that treats visual perception as the constructive generation of internal representations based on very simple, meaningless sensory primitives. The Nobel Prize winning work of Hubel and Wiesel was relevant here, and we'll come back to that later in this module. So that's a very brief introduction to Hebbian learning.